Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics, Volume 1. Motion, Sound, and Heat by Isaac Asimov. Recorded, edited, and produced by JohnLothe. Chapter 1. The Search for Knowledge. From Philosophy to Physics. The scholars of ancient Greece were the first we know of to attempt a thoroughgoing investigation of the universe, a systematic gathering of knowledge through the activity of human reason alone. Those who attempted this rationalistic search for understanding, without calling in the aid of intuition, inspiration, revelation, or other non-rational sources of information, were the philosophers, from Greek words meaning lovers of wisdom. Philosophy could turn within, seeking an understanding of human behavior, of ethics and morality, of motivations and responses. Or it might turn outside to an investigation of the universe, beyond the intangible wall of the mind, an investigation, in short, of nature. Those philosophers who turned toward the second alternative were the natural philosophers, and for many centuries after the palmy days of Greece, the study of the phenomena of nature continued to be called natural philosophy. The modern word that is used in its place, science, from a Latin word meaning to know, did not come into popular use until well into the 19th century. Even today, the highest university degree given for achievement in the sciences is generally that of Doctor of Philosophy. The word natural is of Latin derivation, so the term natural philosophy stems half from Latin and half from Greek, a combination usually frowned upon by purists. The Greek word for natural is physikos, so one might precisely speak of physical philosophy to describe what we now call science. The term physics, therefore, is a brief form of physical philosophy, or natural philosophy, and in its original meaning included all of science. However, as the field of science broadened and deepened, and as the information gathered grew more voluminous, natural philosophers had to specialize, taking one segment or another of scientific endeavor as their chosen field of work. The specialties received names of their own and were often subtracted from the once universal domain of physics. Thus, the study of the abstract relationships of form and number became mathematics. The study of the position and movements of the heavenly bodies became astronomy. The study of the physical nature of the earth we live upon became geology. The study of the composition and interaction of substances became chemistry. The study of the structure, function, and interrelationships of living organisms became biology, and so on. The term physics then came to be used to describe the study of those portions of nature that remained after the above-mentioned specialties were subtracted. For that reason, the word has come to cover a rather heterogeneous field and is not as easy to define as it might be. What has been left over includes such phenomena as motion, heat, light, sound, electricity, and magnetism. All these are forms of energy, a term about which I shall have considerably more to say later on, so that a study of physics may be said to include primarily a consideration of the interrelationships of energy and matter. This definition can be interpreted either narrowly or broadly. If it is interpreted broadly enough, physics can be expanded to include a great deal of each of its companion sections of science. Indeed, the 20th century has seen such a situation come about. The differentiation of science into its specialities is, after all, an artificial and man-made state of affairs. While the level of knowledge was still low, the division was useful and seemed natural. It was possible for a man to study astronomy or biology without reference to chemistry or physics, or for that matter, to study either chemistry or physics in isolation. With time and accumulated information, however, the borders of the specialties approached, met, and finally overlapped. The techniques of one science became meaningful and illuminating in another. In the latter half of the 19th century, physical techniques made it possible to determine the chemical constitution and physical structure of stars, and the science of astrophysics was born. The study of the vibrations set up in the body of the Earth by quakes gave rise to the study of geophysics. The study of chemical reactions through physical techniques initiated and constantly broadened the field of physical chemistry, and the latter, in turn, penetrated the study of biology to produce what we now call molecular biology. As for mathematics, that was peculiarly the tool of physicists. At first, much more so than that of chemists and biologists. And as the search into first principles became more subtle and basic, it became nearly impossible to differentiate between the pure mathematician and the theoretical physicist. In this book, however, I will discuss the field of physics in its narrow sense, avoiding consideration, as much as possible, of those areas that encroach on neighboring specialities. The Greek view of motion. Among the first phenomena considered by the curious Greeks was motion. One might initially suspect that motion is an attribute of life. After all, men and cats move freely, but corpses and stones do not. A stone can be made to move, to be sure, but usually through the impulse given it by a living thing. However, this initial notion does not stand up, for there are many examples of motion that do not involve life. Thus the heavenly objects move across the sky, and the wind blows as it wills. Of course, it might be suggested that heavenly bodies are pushed by angels, and that wind is the breath of a storm god, and indeed such explanations were common among most societies, and through most centuries. The Greek philosophers, however, were committed to explanations that involved only that portion of the universe that could be deduced by human reason from phenomena apparent to human senses. That excluded angels and storm gods. Furthermore, there were pettier examples of motion. The smoke of a fire drifted irregularly upward. A stone released in midair promptly moved downward, although no impulse in that direction was given it. Surely, not even the most mystically minded individual was ready to suppose that every wisp of smoke, every falling scrap of material, contained a little god or demon pushing it here and there. The Greek notions on the matter were put into sophisticated form by the philosopher Aristotle, 384 to 322 BC. He maintained that each of the various fundamental kinds of matter, elements, had its own natural place in the universe. The element earth, in which was included all the common solid materials about us, had as its natural place the center of the universe. All the earthly matter of the universe collected there, and formed the world upon which we live. If every portion of the earthly material got as close to the center as it possibly could, the earth would have to take on the shape of a sphere. And this, indeed, was one of several lines of reasoning used by Aristotle to demonstrate that the earth was spherical and not flat. The element, water, had its natural place about the rim of the sphere of earth. The element air had its natural place about the rim of the sphere of water, and the element fire had its natural place outside the sphere of air. While one can deduce almost any sort of scheme of the universe by reason alone, it is usually felt that such a scheme is not worth spending time on unless it corresponds to reality, to what our senses tell us about the universe. In this case, observation seems to back up the Aristotelian view. As far as the senses can tell, the Earth is indeed at the center of the universe. Oceans of water cover large portions of the Earth. The air extends about land and sea, and in the airy heights there are even occasional evidences of a sphere of fire that makes itself visible during storms in the form of lightning. The notion that every form of substance has its natural place in the universe is an example of an assumption. It is something accepted without proof, and it is incorrect to speak of an assumption as either true or false, since there is no way of proving it to be either. If there were, it would no longer be an assumption. It is better to consider assumptions as either useful or useless, depending on whether or not deductions made from them correspond to reality. If two different assumptions or set of assumptions both lead to deductions that correspond to reality, then the one that explains more is the more useful. On the other hand, it seems obvious that assumptions are the weak points in any argument, as they have to be accepted on faith in a philosophy of science that prides itself on its rationalism. Since we must start somewhere, we must have assumptions, but at least let us have as few assumptions as possible. Therefore, of two theories that explain equal areas of the universe, the one that begins with fewer assumptions is the more useful. Because William of Ockham, 1300 possibly to 1349 possibly, a medieval English philosopher, emphasized this point of view, the effort made to whittle away at unnecessary assumptions is referred to as making use of Occam's razor. The assumption of natural place certainly seemed a useful one to the Greeks. Granted that such a natural place existed, it seemed only reasonable to suppose that whenever an object found itself out of its natural place, it would return to that natural place as soon as given the chance. A stone, held in the hand, in mid-air, for instance, gives evidence of its eagerness to return to its natural place by the manner in which it presses downward. This, one might deduce, is why it has weight. If the supporting hand is removed, the stone promptly moves toward its natural place and falls downward. By the same reasoning, we can explain why tongues of fire shoot upward, why pebbles fall downward through water, and why bubbles of air rise up through water. One might even use the same line of argument to explain rainfall. When the heat of the sun vaporizes water, turns it into air, a Greek might suppose, the vapors promptly rise in search of their natural place. Once those vapors are converted into liquid water again, the latter falls in droplets in search of their natural place. From the assumption of natural place, further deductions can be made. One object is known to be heavier than another. The heavier object pushes downward against the hand with a greater eagerness than the lighter object does. Surely, if each is released, the heavier object will express its greater eagerness to return to its place by falling more rapidly than the lighter object does. So Aristotle maintained, and indeed this too seemed to match observation, for light objects such as feathers, leaves, and snowflakes drifted down slowly, while rocks and bricks fell rapidly. But can the theory withstand the test of difficulties deliberately raised? For instance, an object can be forced to move away from its natural place, as when a stone is thrown into the air. This is initially brought about by muscular impulse, but once the stone leaves the hand is no longer exerting an impulse upon it. Why, then, doesn't the stone at once resume its natural motion and fall to earth? Why does it continue to rise in the air? Aristotle's explanation was that the impulse given the stone was transmitted to the air, and that the air carried the stone along. As the impulse was transmitted from point to point in the air, however, it weakened, and the natural motion of the stone asserted itself more and more strongly. Upward movement slowed and eventually turned into a downward movement, until finally the stone rested on the ground once more. Not all the force of an arm or a catapult could, in the long run, overcome the stone's natural motion. Whatever goes up must come down, we still say. It therefore follows that forced motion away from the natural place must inevitably give way to natural motion toward the natural place, and that natural motion will eventually bring the object to its natural place. Once there, since it has no place else to go, it will stop moving. The state of rest, or lack of motion, is therefore the natural state. This, too, seems to square with observation, for thrown objects come to the ground eventually and stop. Rolling or sliding objects eventually come to a halt, and even living objects cannot move forever. If we climb a mountain, we do so with an effort, and as the impulse within our muscles fades, we are forced to rest at intervals. Even the quietest motions are at some cost, and the impulse within every living thing eventually spins itself. The living organism dies and returns to the natural state of rest. All men are mortal. But what about the heavenly bodies? The situation with respect to them seems quite different from that with respect to objects on earth. For one thing, whereas the natural motion of objects here below is either upward or downward, the heavenly bodies neither approach nor recede, but seem to move in circles about the earth. Aristotle could only conclude that heavens and the heavenly bodies were made of a substance that was neither earth, water, air, nor fire. It was a fifth element, which he named ether, a Greek word meaning blazing, the heavenly bodies being notable for the light they emitted. The natural place of the fifth element was outside the sphere of fire. Why then, since they were in their natural place, did the heavenly bodies not remain at rest? Some scholars eventually answered that question by supposing the various heavenly bodies to be in the charge of angels, who perpetually rode them around the heavens. But Aristotle could not indulge in such easy explanations. Instead, he was forced into a new assumption, to the effect that the laws governing the motion of heavenly bodies were different from those governing the motion of earthly bodies. Here, the natural state was rest, but in the heavens, the natural state was perpetual circular motion. Flaws in theory. I have gone into the Greek view of motion in considerable detail because it was a physical theory worked out by one of history's greatest minds. This theory seemed to explain so much that it was accepted by great scholars for 2,000 years afterward. Nevertheless, it had to be replaced by other theories that differed from it at almost every point. The Aristotelian view seemed logical and useful. Why then was it replaced? If it was wrong, then why did so many people of intelligence believe it to be right for so long? And if they believed it to be right for so long, what eventually happened to convince them that it was wrong? One method of casting doubt upon any theory, however respected and long established, is to show that two contradictory conclusions can be drawn from it. For instance, a rock dropping through water falls more slowly than the same rock dropping through air. One might deduce that the thinner the substance through which the rock is falling, the more rapidly it moves, in its attempt to return to its natural place. If there was no substance at all in its path, a vacuum, from a Latin word meaning empty, then it would move with infinite speed. Actually, some scholars did make this point, and since they felt infinite speed to be an impossibility, they maintained that this line of argument proved that there could be no such thing as a vacuum. A catchphrase arose that is still current. Nature abhors a vacuum. On the other hand, the Aristotelian view is that when a stone is thrown, it is the impulse conducted by the air that makes it possible for the stone to move in the direction thrown. If the air were gone and a vacuum were present, there would be nothing to move the stone. Well then, would a stone in a vacuum move at infinite speed or not at all? It would seem we could argue the point either way. Here is another possible contradiction. Suppose you have a 1-pound weight and a 2-pound weight, and let them fall. The 2-pound weight, being heavier, is more eager to reach its natural place, and therefore falls more rapidly than the 1-pound weight. Now place the two weights together in a tightly fitted sack, and drop them. The 2-pound weight, one might argue, would race downward, but would be held back by the more leisurely fall of the 1-pound weight. The overall rate of fall would therefore be an intermediate one, less than that of the 2-pound weight falling alone, and more than that of the 1-pound weight falling alone. On the other hand, you might argue, the 2-pound weight and the 1-pound weight together formed a single system weighing 3 pounds, which should fall more rapidly than the 2-pound weight alone. Well then, does the combination fall more rapidly or less rapidly than the 2-pound weight alone? It looks as though you could argue either way. Such careful reasoning may point out weaknesses in a theory, but it rarely carries conviction, for the proponents of the theory can usually advance counter-arguments. For instance, one might say that in a vacuum, natural motion becomes infinite in speed, while forced motion becomes impossible. And one might argue that the speed of fall of two connected weights depends on how tightly they are held together. A second method of testing a theory, and one that has proved to be far more useful, is to draw a necessary conclusion from the theory and then check it against actual phenomena as rigorously as possible. For instance, a 2-pound object presses down upon the hand just twice as strongly as a 1-pound object. Is it sufficient to say that the 2-pound object falls more rapidly than the 1-pound object? If the 2-pound object displays just twice the eagerness to return to its natural place, should it not fall at just twice the rate? Should this not be tested? Why not measure the exact rate at which both objects fall, and see if the 2-pound object falls at just twice the rate of the 1-pound object? If it doesn't, then surely the Greek theories of motion will have to be modified. If, on the other hand, the 2-pound weight does fall just twice as rapidly, the Greek theories can be accepted with that much more assurance. Yet such a deliberate test or experiment was not made by Aristotle or for 2,000 years after him. There were two types of reasons for this. One was theoretical. The Greeks had had their greatest success in geometry, which deals with abstract concepts such as dimensionless points and straight lines without width. They achieved results of great simplicity and generality that they could not have obtained by measuring actual objects. There arose, therefore, the feeling that the real world was rather crude and ill-suited to helping out abstract theories of the universe. To be sure, there were Greeks who experimented and drew important conclusions therefrom. For example, Archimedes, 287 perhaps to 212 BC, and Hero, 1st century AD. Nevertheless, the ancient and medieval view was definitely in favor of deduction from assumptions rather than of testing by experimentation. The second reason was a practical one. It is not as easy to experiment as one might suppose. It is not difficult to test the speed of a falling body in an age of stopwatches and electronic methods of measuring short intervals of time. Up to 3 centuries ago, however, there were no timepieces capable of measuring small intervals of time, and precious few good measuring instruments of any kind. In relying on pure reason, the ancient philosophers were really making the best of what they had available to them, and in seeming to scorn experimentation, they were making a virtue of necessity. The situation slowly began to change in the late Middle Ages. More and more scholars began to appreciate the value of experimentation as a method of testing theories. And here and there, individuals began trying to work out experimental techniques. The experimentalists remained pretty largely without influence, however, until the Italian scientist Galileo Galilei, 1564 to 1642, came on the scene. He did not invent experimentation, but he made it spectacular and popular. His experiments with motion were so ingenious and conclusive that they not only began the destruction of Aristotelian physics, but demonstrated the necessity, once and for all, of experimentalism in science. It is from Galileo, he is invariably known by his first name only, that the birth of experimental science, or modern science, is usually dated. And yet, we can regret that the Greek philosophers did not conduct certain simple experiments that required no instruments. For instance, a sheet of thin papyrus falls slowly. The same sheet crumpled into a small, tight ball drops at a clearly greater speed. Since its weight hasn't changed as a result of the crumpling, why the change in the rate of fall? A question as simple as this might have been crucial in modifying Greek theories of motion in what we would now consider the proper direction. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.